Okay, Assalamualaikum and good afternoon. Now we will continue chapter 3, Bipolar Junction Transistor BJT Part 2. So after completing this section, you should be able to discuss how a BJT is used as a voltage amplifier and switch. Okay, now amplification is the process of linearly increasing the amplitude of electrical signals and is one of the major property of a transistor. As you learn, a BJT has current gain called beta. When a BJT is biased in the active or linear region, as previously described, the BE junctions has a low resistance due to forward bias and the BC junction has a high resistance due to reverse bias. Before discussing the concept of transistor amplification, the designations that we will use for the circuit quantities of current, voltage and resistance must be explained because amplifier circuit has both DC and AC quantity. Okay, DC and AC quantity. In this text, italic capital letter are used for both DC and AC current, I, and voltage, V. This rule applies to RMS, average, peak, and peak-to-peak AC values. AC currents and voltage value are always RMS unless stated otherwise. Although some texts use lowercase I and V for a AC current and voltage, we reserve the use of lowercase I and V only for instantaneous value. In this text, the distinction between a DC current or voltage and an AC current or voltage is in the subscript. DC quantities always carry an uppercase Roman non-italic subscript. For examples, IB, IC, and IE are the DC transistor current. VBE, VCB, and VCE are the DC voltage from one transistor terminal to another. Single subscript voltages such as VB, VC, and VE are DC voltage from the transistor terminals to ground. AC and all time varying quantities always carry a lowercase italic subscript. For examples, IB, IC, and IE are the AC transistor current. VBE, VCB, and VCE are the AC voltage from one transistor terminal to another. Single subscript voltage such as VB, VC, and VE are AC voltage from the transistor terminals to ground. The rules is different for internal transistor resistance. As you will see later, transistors have internal AC resistance that are designed for lowercase r with an appropriate subscript. For example, the internal AC emitter resistance is designed for SRE. Internal AC emitter resistance RE. Circuit resistance external to the transistor itself use the standard italic capital R with a subscript that identify the resistance as DC or AC, just as for current and voltage. For example, Re is an external DC emitter resistance, and Re lowercase is an external AC emitter resistance. A transistor amplifies current because the collector current is equal to the base current multiplied by the current gain beta. The base current in a transistor is very small compared to the collector and emitter current. Because of this, the collector current is approximately equal to the emitter current. IC approximately equal to IE. With this in mind, let's look at the circuit in the figure slide. An AC voltage Vs is superimposed on the DC bias voltage VBB by capacitive coupling as shown. The DC bias voltage VCC is connected to the collector through the collector resistor RC. Okay, VCC to the collector resistor RC. The AC input voltage produces an AC base current which results in a much larger AC collector current. The AC collector current produces an AC voltage across RC, thus producing an amplified but inverted reproductions of the AC input voltage in the active region of operations. The forward bias base emitter junction presents a very low resistance to the AC signals. This internal AC emitter resistance is designed R in figure in slide and appear in series with RB. The AC base voltage is VB equal to IE/RE. The AC collector voltage VC equal to AC voltage drop across RC. VC equal to IC/RC. Since IC approximately equal to IE, the AC voltage is VC equal to IE/RC. Since voltage gain is defined as the ratio of the output, okay, voltage gain is defined as the ratio of the output to the input voltage. So the ratio of VC to VB is the AC voltage gain AV of the resistor. So AV is the ratio between VC and VB. Okay, BJT as switch. Figure illustrates the basic operation of a BJT as a switching device. In part A, the transistor is in the cut-off region because the base emitter junction is not forward bias, in a reverse bias. In these conditions, there is ideally an open between collector and emitter. Okay, so collector and emitter, as indicated by the switch equivalence. So this switch open. Okay, so reverse bias. In part B, the transistor is in the saturation region because the base emitter junction and the base collector junctions are forward bias and the base current is made large enough to cause the collector current to reach its saturation value. So IC saturated. In this condition, there is ideally a short between collector and emitter. So this collector and emitter as indicated by the switch equivalent as a closed switch. And actually a small voltage drop across the transistor of up to a few tenths of volt normally occur, which is the saturation voltage VCE saturation. Sometimes we assume VCE saturation is equal to 0. Okay, as mentioned before, a transistor is in the cut-off region when the base emitter junction is not forward biased. So all of the currents are 0 and VCE is equal to VCC. And when the base emitter junction is forward biased and there is enough base current to produce a maximum collector current IC, the transistor is saturated. The formula for collector saturation current is IC equal to VCC minus VCE saturations over RC. When VCE saturation is very small compared to VCC, it can usually be neglected. The minimum value of base current needed to produce saturations is IB minimum for saturation equal to IC saturation over beta. Normally, IB should be significantly greater than IB minimum to ensure IB in the circuit must be greater than IB minimum to ensure that the transistor is saturated. The transistor in figure is used as a switch to turn the LED on and off. For example, a square wave input voltage with a period 2 seconds is applied to the input as indicated. When the square wave is at 0 volt, the transistor is in cut-off, and since there is no collector current, the LED does not emit light. And when the square wave goes to its high levels on, the transistor saturates. This forward bias the LED and the resulting collector current through the LED cause it to emit light. Thus, the LED is on for 1 second and off for 1 second.